Saxon Advanced Mathematics, Lesson 23. Students, we're still talking about functions. We're going to be talking about functions for quite a while. We talked about functions just in general, and that was kind of confusing, right? We have the whole independent variable, dependent variable, domain and range, blah, blah, blah. That was kind of theoretical and weird. And I think it took a slightly better turn when we started talking about specific kinds of functions. We talked about absolute value functions, and we learned that they make a graph that looks kind of like that, right? When you map the pairs of points in an absolute value function, they make this V shape. We talked about reciprocal functions, and we said that, when there's a line that's like this, then the reciprocal function kind of goes like that, right? There's this weird inside-outness kind of the two of them, right? So that's what I want you to take away from this, is that functions are just equations. There are certain groups of them, and when we map the inputs and the outputs to similar kinds of functions, we get similar kinds of pictures, okay? And we've talked about those too. Of course, we've talked about linear, and I kind of included that right there, right? A linear function is a line, right? And so what we're going to be doing for the next handful of lessons, really through a lot of the book, we're going to just be talking about different kinds of functions, what they look like, how to sketch their graphs, how they behave with numbers, and they're all within the family of functions. Today's topic is exponentials. And they're fun because they have a very distinct shape. They go either like that or like that, okay? And we'll look at this and talk about them in just a second. That's what we're doing. The one thing that I want you to remember is that when you're trying to calculate these functions and then graph them, it's really helpful to use a chart to sketch them. And we're going to do that in this lesson, so you'll see what I mean. But this makes it easier to wrap your head around these different topics, right? Sometimes this will all start to feel as kind of scrambled. Just draw yourself a chart and slow down, and you'll get it figured out quite nicely. All right? So let's look at our first example here. And what we're going to do is just get a feel for how exponential functions generally work. Here is a classic exponential function. Y equals 2 to the x. This is what makes it an exponential function. Our variable is in the exponent, okay? We've had variables with exponents on them, but we've never had the letter in the exponent before. That's what makes this different. So we want to graph this, but we'll first start by making a chart. We'll pick some x values. We'll think strategically about how to do that. And we'll calculate it, and then that will give us our y value. Okay, so whenever I see an exponent like that, I think about two things. I think that if you put the exponent of 0 on, you're going to get an automatic answer. And if you put the exponent of 1 on, you're going to get an automatic easy answer. So let's try that. Let's let x equal 0 and 1 first, because it's kind of like those two, right? So this would be 2 to the 0 power, right? Because the x value goes up in the exponent. 2 to the 0 power, well, that's going to be equal to 1. Oh, that's pretty easy. to the first power, that would be 2 to the 1, that would be 2. Look at that, we've already got 2 values really fast. And let me add a third one to this. X to the negative 1 equals 1 over x. Let's add that to our list of easy things to calculate. Two to the minus 1 would be 1 over 2, right? 1/2. Okay? And then let's just throw in this one. 2 squared equals 4. And I want to do one more. Minus 2. That would be 2 to the minus 2, and that would be 1 over 4. Okay. May I suggest that whenever you're doing exponential functions, these are wonderful values. I'm going to go so far as to call them ideal values to use for an exponential function, all right? So if you ever have a function that has a variable in the exponent, start thinking in terms of these independent variables to plug in and solve. Now we're ready to graph. Now here's a cool thing about exponential functions. You're not going to use the bottom half. You can just draw the top. So I'm going to draw this as carefully as I can to keep the scale right. And now let's plug in these variables, right? We have the x and the y. We'll just match those and graph them and see what we get. 0 and 1. That's that point. 1 and 2. 1 and 2. Minus 1 and 1/2. Okay, that's kind of hard to graph, but minus 1 and 1/2. 2 and 4. 1, 2, 3, 4. Minus 2 and 1/4. Okay, that's even harder to graph. But these values do a great job of showing us the way an exponential curve works. Now, here's what I want you to notice on this. This is an asymptote. It's never going to touch. It looks like it's touching on mine, but it will never touch here on the x-axis. On the y-axis, it's going to shoot up on a very steep curve. That's the exponential growth that we're talking about. There's our x and our y, just to orient you. Okay? This point, see how I made it extra big? This point is the all-important 0, 1, and that will always show up on our exponential curves because x to the 0 is always equal to 1. So this point is really important, and you'll see why. I'll explain more about that. But I want to point that out to you, that that curve is very important on this. All right, let's do another one. Example 23.2. And this time, John gives us something that looks quite different. Last time he wrote y equals 2 to the x. And look, this time he writes it like this. It's perfectly fine. This is basic algebraic notation. This is functional notation. It's the same difference. It works exactly the same. We just notice that this means the very same thing, right? It's sort of like a sentence where you said Bill is coming also or Bill is coming too. The words also and to look very different, sound very different, but they mean exactly the same thing. That's what I want you to take away from this. Before I go into that problem, I want to show you this in the book though. These sketches, it's on page 168. I highly recommend you tag it with a page like this. This will help us see the way exponential exponential equations or exponential functions will always graph. This is like the one that we just did where our equation, our variable was on a base greater than 1. They will all have the asymptote on the negative side of the x-axis, and then they will shoot up. The larger the number that we're putting the exponent on, the steeper the curve will go up. If our base is a fraction, the curve will be the mirror image. Here the asymptote is on this side, and they're all curving up over here. Again, well, the smaller the fraction, the higher the curve. All right? But here's one thing I want you to notice, and this is what I talked about just a second ago. All of these curves pass through the point of 0, 1. Look at that. Every single one of them passes through that very same point. If we laid these two pictures on top of each other, all of them would be, this is like the Grand Central Station of exponential functions. They all pass through there. Grand Central Station, you West Coast children might not know, is a train station in Manhattan, downtown New York, where all the trains meet up. It's a very busy place because so many lines come in together there. So that's where that expression comes from, is Grand Central Station. That makes me want to find a video and show you how that what Grand Central Station looks like, so you can see all of the, everything's passing through this common point. So when we're sketching exponential functions, we know that this point 0, 1 will be at the center. We know that if our base is a number greater than 1, it will curve up to this side. We know that if our base is a fraction, it will curve to this side. That takes a lot of the work out of graphing these, and I'll show you in this next example how we can do this without having to make a great big chart. So we're going to not let this functional notation scare us. We're going to graph this. We know that we'll need something that looks like this. I'll put in some markers. We know that the base is greater than 1, so we know it's going to be essentially this shape. We know it's going to pass through 0, 1. That's automatic. We know it for sure. And we know that if we plug in a 1 here, then, let me write it down. We know that the f of 1 equals 5, right? Because if we put 1 in here for 5, or 1 in here for x, that's 5 to the first power, that's 5. So we can graph this one as well. If it's 1, then it's 1, 2, 3, 4, 5. Right? That shows us how steeply our curve is going up. We know that this side is just going to trickle down into an asymptote. We don't even have to find values for that. Oh, I didn't make it go steep enough. All we really need is to graph 0, 1, and then find the first power, and then that's good enough. That's all we need. Okay, so and then we can call this the f of x equals 5. And we did it just using 2 points. One we had automatically, and the other one we were able to find with just the simplest of calculations. So we don't have to do that whole chart every time because we remember the fundamental shape of the exponential function. There's an asymptote on one side and then it shoots up on the other side. We can easily calculate the first point on the shoot by finding the base to the power of 1. All right, that makes our job much easier. And let's do one more. And this is the end of this lesson. It is sketch the function of y equals 0.25 to the x. Okay, so we're going back to the algebraic notation here. We're not using the functional notation. It doesn't make any difference in the problem. Bill went also, Bill went too. What I like to do though is I like to rewrite this as a fraction, okay? If you want to do decimals, you can, but my brain is wired to see it better when it's a fraction. Immediately I know, okay, it's going to be the reverse of this kind, right? It's going to, I'm imagining that picture in the book. I know that when the base is a fraction, they go up on the left side and the asymptote is on the right. So I can start thinking about this right away. I know that this magical point of 0, 1 is the grand central station of all basic exponential functions. We'll talk about exceptions to this rule later. Sometimes we can shift the curve, but right now we're not dealing with that. I know that this is a fraction, so I know it's going to go up on this side, and this side is going to be the asymptote, so I can just sketch that. Try to make it as accurate as possible. And then I just find one value. I just want to find the value of x equals 1. When x equals 1, then y equals, oh, I'm sorry, I want to find -1 because I know it's on this side. When y equals -1, when x equals -1, y equals 4, right? Because it's the reciprocal of 1/4. So when y equals -1, x equals 4, 1, 2, 3, 4. And so there's the way my curve looks going up. All right? Let me make sure that you understand how I simplified this because my words tumbled over themselves. If our function is 1/4 to the x, and I choose -1 because I know my curve is going to go up on this side. So that's why I know I want to choose a -1. +1 doesn't interest me because I know that's the asymptote side. My base is a fraction, so I want to choose on the negative sides. That's where the more interesting work is. So I choose -1. 1/4 to the -1 means I take the reciprocal to find y, right? It's +4. The negative just flips it. So -1 and 4 is my second point. And that's all I need to draw the curve. All right? And I can call this curve y equals 0.25 to the x. That's the name of that function or curve. We know that it passes the vertical line test, right? Because there's no way to draw a vertical line that would hit more than one point. And we know it passes the horizontal line test because no 2 points are the same. This is always curving down. This looks flat, but technically it's curving infinitely. It's curving infinitely, yes. So it passes the horizontal line test too. So it's a one-on-one mapping. It's a one-on-one function where every value of x has a unique and different value of y. It's all coming together, you guys. This function stuff is all starting to become one big set of ideas, and that's my challenge, is to help you knit this idea about functions into all these other problems. So you'll see that functions are just the way we breathe in algebra. We've already been doing it, but now we're going to just talk about it a little more specifically. But it's nothing new. It's all the same of what we've been doing. Okay, that was confusing. Feel free to ignore it. Goodbye.